So now we have studied the different processes, the work done, and also we derived the work done for the isothermal irreversible process, right? Now let us try to derive the work if the isothermal process is reversible instead, not irreversible but reversible. So for that, if you want to find the expression, then let us take the n moles of ideal gas and we are placing that in the cylinder, right? Okay, so here again we are taking the same situation as we took earlier. N moles of ideal gas we took, and piston is frictionless and weightless. Earlier also we were having the piston and we were expanding the gas, right? If you remember. So we took the initial pressure, P, initial volume, V1, final pressure, final volume, that we took. So here also let us take the same thing. Initial volume, let us take V1 for the piston. So let us take first of all a cylinder, and inside that cylinder the n moles of ideal gas is there and the piston is fit up. Here you can see in the diagram. And in this diagram, if we see that some volume is there, this volume, initial volume, and this volume suppose is V1. This volume is V1 and pressure suppose is P. Okay, so initial volume is V1 and pressure is P, and we are taking again the expansion case. Okay, so expansion case we are taking. So initial volume and initial pressure is V1 we are taking, and it is expansion, so that's why final volume is little bit higher, correct? External pressure is slightly smaller than the pressure of the gas, so that's why it is able to expand. This is reversible work. Reversible is not fast, this is slow process. Reversible process is very slow process, already explained you. It means what? Means the inside pressure P inside is almost same as P outside, just P inside is slightly greater than P outside, like that. Okay, now you tell me one more thing, that volume we took earlier was V1 and now let us expand it. After expanding, it is increased by some dV, and now after increase it has become new volume. So new volume is slightly greater than initial volume by dV amount. Now let us push further. The gas will further push the piston. Now let us increase it little bit more. Okay, so this has increased further now. So this is also, let us call this also dV only. So earlier it was dV, now also this is dV only. Okay, in this process and dV finally it has reached to this state. Okay, so this state final, if we see, so this is not just two steps, there are a lot of steps happened, and in this way dV we are going ahead, and this is the final step. In the final step the pressure is of course the same almost, but the delta V, the volume change, initial and the final, initial volume and the final volume change, let us take as delta V. So what is the final pressure? Final pressure is P only, but the final volume is V2, and the value delta V is the change in the volume. So final volume is V2 and final pressure, as I told you, little bit smaller, so almost same as the initial but little bit smaller is there. So let us call it P minus dP final pressure, P minus dP. So if it is P minus dP final pressure and the final volume is V2, then let us calculate the amount of work done. Amount of work done is minus P external into delta V, right? What we have earlier studied. So let us use the same formula in the very small section. So for small section we can call the same work done for the small section as dW, which is equal to minus P external into dV. The small volume change is GV, and P external is how much? P external is little bit lesser than P, So P minus dP, P external is P minus dP. We have already written that. So let us put it here. dW is equals to minus of P minus dP, we are putting it here, into dV. P minus dP into dV, we are keeping it. And if we put it here, then what will happen? It will look like this. dW equal to minus of P minus dP into dV. Let us multiply. So minus of P into dV minus plus dP into dV. So minus P into dV plus dP into dV. And dP is very small. And dV, of course, these are incremental changes. These are very small step changes. So dP is very small and dV is also very small. So the two very small numbers are multiplied. So result is negligible, even smaller. So we can neglect that product dP into dV, isn't it? And if we neglect this, then what we get? dW equal to minus P into dV. And this time P is not external pressure. This time P is not P external. This time P is P gas, P internal, right? So please understand that formula was P external, but why we are using the gas pressure, internal pressure? Due to this reason, because dP into dV got neglected. That's why we are using that. So now dW equal to minus of P dV, and this P is not external pressure. This is the gas pressure. So gas pressure means gas equations are also valid. Okay. So let us try using the gas equations, and we can calculate using that. So dW, please remember till here, dW is going to be equal to minus of P gas into dV. So work done, how to calculate now? So work done in the entire expansion from volume V1 to V2 will be how much? Because that was a small work done. See, this is what? Small work done is there, dW. This is not the total work done. Total work done, how to calculate? Total work done, if you want to calculate, so expression for the total work done would be, if we integrate it. If we integrate, then only we can get the total work done. So dW will be integrated from position 1 to 2, and this PdV on the other side, minus PdV, is integrated from V1 to V2 volume, right? So dW has become W, right? After integration, dW has become W, dx becomes x, so dW has become W. So maximum work done we are calculating, and here on the other side, minus P into dV is there, and we want to calculate that. So maximum work done is minus P dV integration from V1 to V2. And as I told you, this is not the external pressure. This P is not the external pressure. This is the inside gas pressure. So if it is inside gas pressure, so PV equal to nRT gas equation can be applied. So if that is applied, so P can be calculated as nRT by V. You will say, why you are using the gas equations? Why one can't we directly do? We cannot do directly because P is a different variable. This is also variable. This is not constant that we can take outside. V, volume, again variable. Integration is a very great tool and it can do summation of so many things. But one limitation is there in the integration. Limitation is that you can't integrate if the thing which is inside the dx or dv with which you are integrating, with which parameter you are integrating, and in the expression some other parameter is changing. So here you are integrating with respect to volume, but your volume is not written here, your pressure is written here. So pressure, how will we able to integrate with volume? That is not possible. Only possibility was if pressure would have been constant, so P could be taken out. Otherwise, we cannot solve this kind of question if P is a different variable and dV is a different variable, because dV we are finding, so V is also changing. So both are changing. So we cannot calculate the direct integration. We have to convert P in terms of V. That's why, that is the main reason why we are using this formula. Many students ask why we can't directly do, why we use that formula. So we use this formula to convert everything into the single variable. Why we are saying that single variable? You will say why nRT is also there. So why you are saying single variable? nRT is a constant. That's why I am calling it a single variable. Because n is constant, r is constant, t is constant. So nRT by v has only variable v, nothing else. Okay, so that's why we are calculating it. nRT by v dv and minus sign is there outside. So after we put this, let us try to put it, then what will come? In place of p, we are putting as minus sign is already there. So nRT by v, because PV equal to nRT, ideal gas equation is there. So P would be how much? nRT by v, and we are putting it here. So it has become nRT by v into dv. As I explained you that nRT is constant. So constant can be of course taken out of the integration. So it will become like this. So if nRT is taken out, so only what is variable is inside, that is v, and there is no other variable inside, no, not even constant. All the constants are taken out. Inside there is nothing else other than v. So we can integrate it. If it is v, so v square by 2 would be the integration, but it is not v. This is 1 by v. So for 1 by x, the integration is ln x, ln natural log of x. Similarly, if it is 1 by v, then the integration would be ln v from limit of integration from v1 to v2. Because 1 by x dx is ln x, so 1 by v dv is ln v from v1 to v2. And how the limits are solved? In the integration, first of all, we put the upper limit minus, then we put the lower limit. Like, we'll put in place of v, first of all, v2. So ln v2 will become minus. Now this time we'll put v1 in place of v. So minus ln v1 has become. So minus nRT into ln v2 minus ln v1. That will come out. Okay. So please remember this. Very simple. The work done is minus nRT ln v2 minus ln v1. You will say, but there is a property of log that log b, a minus log b is log a upon b. So that we can use here. Ln v2 minus ln v1 is ln v2 upon v1. That we can directly use. Okay. So this is how the work done is calculated. Ln v2 by v1 it has become. So the formula, please remember now, this is very important. And ln can be converted into log. What is the formula? Ln x is equals to 2.303 into log x. Ln can be converted into log by this formula. Please remember, this is very important. And what is, if the temperature is constant, then how we do? If the temperature is constant, then we have pressure into volume. That product is also constant. So that also we can use later. But first of all, we have got minus nRT ln v2 by v1. That can be written as minus 2.303 nRT log v2 by v1. That we can write. And what else? As I told you, in this process where the temperature is constant, this is isothermal process. So pressure into volume, the product is constant, and product, if it is constant, then it means that the pressure and the volume are inversely proportional to each other. In this process, not everywhere, in this process, pressure and volume are inversely proportional. So it means if they are inversely proportional, so P1 V1 can be written as equal to P2 V2. And first of all, this is the formula is there. And then after we write P1 V1 equal to P2 V2, then V2 by V1 can be written as equal to P1 by P2. So we can get the new formula from there, because V2 by V1 is becoming equal to P1 by P2. So new formula has become minus 2.303 nRT log P1 by P2. Earlier it was log V2 by V1. So this formula, please always remember, is very important to remember the formulas. Okay. So now the next one is work done we have calculated in all different type of processes. Only adiabatic is left. Otherwise we have done isothermal, reversible, isothermal, irreversible. We have done isobaric. We have done isochoric. Now, other than doing all this from the equation, can we also do by some other method? The work done can be calculated by graph also. Do you know that? Graphical explanation how to calculate of the maximum work done. Graphical explanation means you have to first of all draw the indicator diagram. What is indicator? Indicator diagram is PV diagram. PV diagram is called indicator diagram. So if indicator diagram or PV diagram is drawn, then you have to see the area under PV graph with volume axis. What I am writing here, please write down. This area, work done basically is equal to area under PV graph with volume axis. Okay, area under PV graph with volume axis. So whenever we draw the graph, we have to see the 2 points. First of all, the initial and final state, and during journey from initial to final state, whatever area we can draw with volume, that area will give you the work done. Very simple. So first of all, let us draw the graph before calculating the work done. So the graph in this isothermal irreversible process, different type of processes are there. So isothermal process we are taking. So in isothermal irreversible process, what is the graph? Initial point let us call as A. If the initial point is A is having the coordinates as P1, V1, and after some time we have got the new point, a new state. Of course, the new state is point B, which is P2, V2. So A point to B point journey. If we are going through different processes, then different graphs would be found. So here let us take isothermal graph. So isothermal graph A to B journey, we are first of all writing the coordinates P1, V1. P1 is the height, V1 is the x-axis distance. Similarly, P2, V2 also. And if the system is going from A to B, then what will happen? Work is done or not? Volume is changing, yes or no? Volume is changing. So if the volume is changing, then work is done. Very simple to understand. If the volume is changing, then work is done. Perfect. So if work is done, then how to find that work? So we know that the P external here is equal to P final, which is equal to P2. Why? P external, why it is P2? Because finally it has become, the pressure has decreased a lot. So minus P external into delta V is there, which can be also written as equal to P final or P2. And so graphically the work is what? Below P and V axis, below PV graph basically, and with the volume axis. With the volume axis. Always take with the volume axis. Graph, whenever you are calculating the work, always take with volume axis. With volume axis. Okay. Then whatever area is coming, that will give you the work done. So here this area will come. You will say not only this, there is some upper small area is also there in the corner. That should also come. Okay. So that should also come. But because it is irreversible process, so irreversible process is not here. Every time pressure is not equal to the external pressure. Only the final pressure is equal to external pressure. In irreversible process and reversible process, that is the only difference. And in reversible, whatever reversible is there, that is very slow. So every time the pressure is equal to the external pressure. But here in the irreversible process, it is not. So external pressure is final pressure. External pressure is final pressure. Please remember. If here you are doing in this, then P external is P final. So P external is P final. So only this area should come. No other area should come. And how do we calculate that? By very simple method, minus P external into delta V. So area under the graph we are finding first of all. So work done is equals to area under the graph. So this is a rectangle. So rectangle is equal to length into width. So P2 into V2 minus V1. This is the area, of course. And sign convention is there. So sign convention we will put, of course. So what will happen? The work done is calculated. Work done is calculated. So let us go from A to B. So A was having P1 V1 as the pressure and B was having P2 V2 as the pressure and volume. So suppose the process is taking 4 steps. 1, 2, 3 and 4. Process is taking 4 steps. So in these 4 steps you can see from 1 to 2 we went, and from 2 to 3 we went, and 3 to 4, like that. Why we are dividing? We are able to divide it because the process is fast, of course, because it is irreversible. But if the process is slow, then it will take many steps in going from A to B. So we are just taking the example of dividing in the 4 steps. So if we go step by step, then we will calculate the work done also step by step, isn't it? And we will try to add all the work done later on. So from 1 to 2, this area will take, this area will take, isn't it? That area is going to be taken. Of course, it is not the full area, but this area will take. And from 2 to 3, this area will take. 3 to 4, this area will take. And next also up to B, this area will take. So all these small areas are there which will be taken. So let us take all of them. Yeah, we are taking them, and we have taken, yeah, all the what was there, in which all of them what we have taken is the final pressure is taken as the total pressure throughout the pressure. Final pressure is throughout pressure. So that only external pressure we are equating with the final pressure, and we are calculating the smaller and smaller step areas. And you can see if we divide the system into the steps, the total area has increased. Earlier we were leaving a lot of portion as the vacant, but in this time when we have divided the process in 4 steps, then we are able to include much more area than before, right? That's why the explanation is basically, I want to explain you that when you divide the system in finite steps, then your overall area increases. Your work, you can get more work done basically. So that will increase. So in the same process, suppose you are considering that this is not happening from P1 V1, which is the A point, it went to the B point, but the process is isothermal and reversible. If it is reversible, so now it is not going very fast. Now it will go very slowly from A to B. It will take infinite steps to go from A to B, right? This is small step we have taken, and then the next step we will take, and slowly it will go, because it is infinite step process. And this time the system is reversible. Reversible means it will go very slowly, as I gave you the example of crossing the river while walking on a small bamboo was there, and we were crossing the river while walking on that bamboo because other side was a danger. So that's why we came back also slowly. If we go slowly, then all the areas are able to be included. None of the area will be left. Small changes if we do, we will take fully. Area, none of the area is left. When we go too fast, many things become haphazard or messy. But if we go slow, then things their normal position, right? So that's why we should go slow to get more area. If we are going fast, then much more area will be left unshaded. Shaded portion is more in the second case. Work done would be more than irreversible work done. Work done is maximum in the reversible case only. Okay, so now let's try a few questions because we have discussed a lot of the things now. So you tell me, what is the formula of work done? Tell me. I just gave you the formula, if you remember. Now let me give you the options. Is it this the formula of work done? Minus P external into delta V, or minus P delta V, which is the formula of work done, or minus P dV? What? Or all of these are correct because all seems similar to you, huh? No, all are not same. So what do you say? Which one is correct? You will say, sir, this in this solving minus p external into delta v looks logical, but why dv, why the C option is there? Because the work done formula is not in terms of dv, it is in terms of delta v. But for a small change, so which one of these is correct? Which one is correct here? What do you say? So minus p external into delta v is there, that is also work done, isn't it? And minus p delta v we have done, that is also work done, minus p delta v. And dv, minus p dv, isn't it? That is also work done. It's not that the minus p dv is not the work done, not like that. That is also work done, minus p dv. So if we take all of these work dones, then how we will come to the conclusion? What is the final answer then? All of these, correct? All of these is the answer. So fourth option we will say as the correct option, right? So here in this situation we have got the fourth option as the correct. Now let's see. First of all, let me show you all these formulas which I gave you. So from looking at that position, we can see that all of these are correct. So done. This one is we have done. And the next, let me give you one more example. So formula of maximum work done is, so what is the maximum work done? Minus nRT ln v2 by v1. Is that the maximum work done? Or minus 2.303 nRT log v2 by v1. Is that the maximum work done? You will say, why you are talking about the maximum work done? Why don't you just talk isothermal work done? No, in the isothermal process, the work done is maximum. So that's why we are talking about the maximum work done. In isothermal process, you could see that none of the area was left kept empty. Every area, by small selection, small increment or decrement, every portion of the strip is taken consideration of. So that's why this work done, all these three options looking are correct, isn't it? Because p1 by p2 is also possible, which can be replaced with v2 by v1. So all of these are correct. Please remember this, and I'm showing you the thing where I explained you this particular thing, that minus nRT into ln v is there, and minus 2.303 nRT log v2 by v1 is there, and also p1 by p2 is there. So please understand all this and practice more and more questions. In the next class, we are going to start a very important section, first law of thermodynamics, in this next class, and we will go in details of that, while also going about the expressions and the sign conventions and how the problems are framed from the first law of thermodynamics. That all we will see in the next class. So see you in the next class then. Okay, bye.